In this video, we'll be looking at Taylor series expansions and also the binomial series. Although I'm not sure we'll get to the binomial series in this video, but in this couple videos we'll get to it. I would say this is really the reason we talk about series at all. In previous sections, I've employed some rather indirect reasoning to connect a function to its corresponding series representation. Right? Been fortunate enough to get the geometric series to connect. But this following result, this theorem due to Taylor, gives us a much more sort of universal approach. And here it is. It says that if a function has a power series representation, so if I can write f of x as a power series in some domain, then the coefficients are actually given by the values of the function's derivative evaluated at the center point divided by n factorial. In fact, we can write the function as the sum n equals 0 to infinity of the nth derivative evaluated at the center divided by n factorial times x minus a to the n. This formula is actually a generalization of the tangent line approximation that we saw in Calculus 1, as I'll make much more explicit in a future video. But here's the actual, so the notation is f parentheses 0 of x, that means f of x. That's a definition. And so if I write out the first few terms here, it is actually f of x is f of a plus f prime of a times x minus a plus 1/2 f prime prime of a times x minus a squared plus dot 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 dot. So, I don't know, you may or may not recognize these first two terms as nothing more than the tangent line approximation to y equals f of x centered at the point of tangent CA, comma f of a. Alright, so to prove this, basically we just use term by term. The hard part of the idea here is the existence of the series, but if it exists, then showing that such a series must match the derivatives of the function at the center is relatively simple. To start with, if we have a power series, centered at a for f, if we plug in a, this is 0, that's 0, that's 0, and all we're left with is c sub 0. So f of a is c naught. Then if you differentiate this series term by term, you get rid of the c naught and you got c1 plus 2c2 and so forth. Again, if we plug in x equal to a, all these things are 0 and we're just left with c1, which shows us that c1 is f prime of a. Differentiate again, we get 2c2 is 6c plus 6c3 times x minus a plus dot 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 dot. This tells me that f prime prime of a is 2 times c2. And you can see that if we differentiate 3 times and then plug in a, we get f prime 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 of a is 6c3. Of course, this is 3 factorial, that's 2 factorial, that's 1 factorial, that's also 0 factorial, which is by definition 1. And so you start to see the pattern. If we differentiate n times, right, then n times we get this plus, oh well, let's just say here. So I was just doing term by term differentiation of the series which exists, which gives me that. And I don't know. I think this is probably convincing enough already, but generically speaking, I get that. After n-fold differentiations, I reduce the power by n, and I get the multiplication by this out front. And so, in short, if I take the nth derivative and plug in a, this is 0 except when k is equal to n, and when k is equal to n, that's just a minus a, which is 1 to the 0, which is 1, and this gives me an n factorial times cn. So we get the nth derivative evaluated at a as cn times n factorial. Therefore, cn is fn, the nth derivative of f at a divided by n factorial as claimed, and if we plug it back into f of x, we find the Taylor expansion of f centered at a. Alright. All of this is assuming f of x has a power series expansion. Alright. So when a equals to 0, the Taylor series expansion becomes the Maclaurin expansion, and this is the Maclaurin series expansion of a function centered at 0. Again, assuming that it exists, that the series expansion exists. So for any differentiable function, it's fairly clear we can construct a Taylor series for that function, right? I say differentiable, but I probably should say I mean, this language is, to be more precise, smooth. In other words, not only can we differentiate it, we can differentiate it infinitely many times. And so we just differentiate and evaluate, and you can construct a Taylor series, right? So if f of x has a power series expansion, then it must match the Taylor expansion. But there's a deeper question that we should ask, is given a differentiable function, when does it have a Taylor series expansion? Does it always have one? Well, actually no. The next example after the theorem below illustrates a function which, although is infinitely differentiable, it doesn't actually have a Taylor series expansion. That's a subtle example, but I feel like we should get it out of the way before we go on. Here's Taylor's theorem. If f is differentiable at least n plus 1 times on an open interval I containing a, then for each x and I there exists a c between x and a such that this holds, where Rn of x is the remainder, and that remainder term can be written in terms of the evaluation of the n plus 1th derivative at some point c as described above, divided by n plus 1 factorial times x minus a to the n plus 1. All right, and when Rn of x goes to 0 for all x in the interval, as n goes to infinity, we say that the Taylor series generated by f converges to f on I, in which case f of x is equal to this. So Taylor's theorem does a little bit better than our previous theorem. Now it's saying that it's giving us a criteria. If we can, show that this remainder term goes to 0, then we get that the function is matched by its Taylor series. Actually showing that such a c exists for arbitrary n is kind of a hard problem, though. Here's a counterexample to the, well, not a counterexample, but an example of, it's pretty much the only nice, easy example there is to. Here it is. You do e to the minus 1 over x squared if x is not equal to 0, and 0 if x is equal to 0. So you could also make it e to the minus 1 over x squared if x is positive, and x equal to 0 if x is negative or 0. That would work just the same. So anyway, you can show that this function has derivatives of all order, and in fact all of the derivatives of this function are 0 at 0. So when you generate the Taylor series at 0 for the function, you get the function which is identically 0, and yet this function is not identically 0 near 0. So this is an example of a function which is smooth but not analytic. So I was still, when I wrote these notes, working out my own. Some people say differentiable for smooth. It's unfortunate, but I think smooth is more descriptive. When I say differentiable, I just mean one derivative exists. So anyway, how many times am I going to have to fix this? All right, I'll get on with it. Anyway, this doesn't have much to do with calculus 2. This is just some background. Well, I can't really say that. It does have to do with calculus 2. I just don't have a good way of testing on it. Let's just say that. All right. So Taylor's theorem is in fact a generalization of the mean value theorem, and much like that theorem, it only tells us that there exists some c, but actually how to find the c such that Rn of x is equal to that. Well, that's tough. This much we can say is we also have Taylor's inequality. If the n plus 1th derivative is bounded by m for x within r units of a, then the remainder of the Taylor series is bounded as follows. So this gives us a way, if we can bound the n plus 1th derivative, then we can squeeze the remainder to 0 and hence show that the function's analytic. That's pretty nice. I'll let you see the text for the proof of that. Although I think I have a proof of that in a future video, so we'll see that. I have a proof of Taylor's theorem in a future video where I actually go through the modification of the mean value theorem proof, but I'm not going to do that here. We're gonna use Taylor's theorem, and we'll get back to the proof later. Okay. So with Taylor's inequality, we no longer need to calculate Rn of x explicitly. We just can, if we can just bound the nth derivative, then we're off to the races. So so anyway, we're not actually going to do that. And in fact, I won't usually ask you to do it either. What I'll say is I usually try to use language like, assuming the function has a Taylor series expansion, find it. And so that's basically freeing you from the task of showing that the remainder goes to 0, right? So here's such a calculation. Let's look at f of x equals to e to the x. Then you can calculate derivatives of all order are just e to the x. So the Taylor series about 0 for e to the x is pretty simple to calculate. It's just f to the nth derivative at 0, which is just e to the 0, which is 1, divided by n factorial by Taylor's theorem. And so there you go. The Taylor series expansion for the exponential, just x to the n over n factorial, n equals 0 to infinity. That is, of course, the Maclaurin series for the exponential. All right. So often it's useful. Let me just write out the first few terms. So we have e to the x is 1 plus x plus 1 half x squared plus 1 over 3 factorial x cubed plus dot 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 dot. This is a wonderful formula, this power series expansion for the exponential. It allows us to do things like calculate e easily, like if you do e to the 1, this tells you that the number e will be equal to 1 plus 1 half plus 1/6 plus dot 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 dot, and it's pretty easy with just a little bit of arithmetic to see why you get e what it is, right? So you can already see that it's 2.5 plus 1, that's 1/6, which is what, 0.1666, so it's like you already got the 2.66, which is awful close to the 2.71. I don't know, I think it's really quite beautiful how easy it is to derive the power series for the exponential. All right. Now again, to be more rigorous, we ought to prove that the Taylor series for e to the x does converge to e to the x. This amounts to showing that Rn goes to 0. I've done that. It's hard. Well, I guess this is not hard. It's just tedious. Now sine of x, we can find the Maclaurin series for sine of x, because if we differentiate sine, we get cosine. Then that gives us minus sine, differentiating gives us minus cosine, differentiating gives us sine. So we got this fourplicity. So the nth derivative of sine x is either plus or minus sine x, right? Plus or minus sine x, or stupid scanner let me down. Or cosine x, right? And you can see, in fact, this one you can actually calculate the, you can bound the nth derivative without much work here, right? It's less than or equal to 1. So we can actually prove that by Taylor's inequality the remainder goes to 0, which shows you that the Taylor series we're going to find for the sine function is in fact a representation of the sine function for all x. All right. But sine and cosine are kind of the only nice examples I know of this that aren't just stupid. But all right, anyway, setting aside the remainder discussion, so we use Taylor's theorem, nth derivative evaluated as 0. Now sine of 0 is 0, so all of the even terms which have sines go away, and we're just left with the odd terms which have plus or minus cosine. So we get cosine of 0, and then cosine of 0 over 3 factorial, you get plus minus, so you get x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, and so forth and so on. There you go. That is the Maclaurin expansion for sine of x. Anyway, I will try to stop talking about existence for now. Let's assume it's not an unreasonable step for most functions. We're just going to assume that a power series representation exists and go about finding it. F of x equals cosine x. We differentiate again and again and again and again. So we either get cosine or sine. Evaluate at 0. We get 1, we get 0, we get minus 1, we get 0, we get 1. And voila, there's the power series expansion for cosine. 1 minus 1 half x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th. Da, 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 da. Again, using Taylor's theorem. All right. Example 5, geometric series. So Now we already know that this is the geometric series, right? But let's see if we can reproduce the result for the geometric series using Taylor's theorem, right? So here we go. Derivative is 1 over 1 minus x squared. Why is it not minus? This is reciprocal, right? Oh, but remember the chain rule. It says differentiate the inside function, which in this case is 1 minus x. So the minus from the chain rule and the minus, because this is the minus 1 power, cancel out to give us a plus 1 over 1 minus x squared. And then differentiate again. We bring down minus 2 times minus 1, which is 2. And then we get a 3 times 2 times 1, and so forth. At the nth derivative, we get, in fact, n factorial over 1 minus x to the n plus 1. And so when you evaluate at 0, you get n factorial. So what happens? Taylor's theorem. All right, we get f to the n, the nth derivative at 0 divided by n factorial, which is n factorial over n factorial, which is x to the n. No surprise there. We already knew that this is equal to that by the geometric series result, but I find this comforting that Taylor's theorem works together to give us the same answer. Right? It would be somewhat troubling if when we did mathematics we got different answer depending on the method we used. So I would hope that we'd give up on our methods if that happened. Not like other branches of science which insist on basic theories which are mutually contradictory and expect us not to be bothered by that. Let's see here, I'm mostly talking about psychology. Anyway, cosh x is, physicists also will admit that their basic foundational theories are inconsistent, but they own up to it, and they say there's something wrong, and something needs to be found out. I shut up. All right, anyway, cosh x is this, sinh x is that. We differentiate, and derivative goes to here, derivative goes back to here. It's a vicious circle of differentiation. Cosh to sinh to cosh, cosh to sinh to cosh. All right, anyway, so if you look at it, we've got cosh, derivative, right? So evaluation at 0 gives me 1, and then 0, then 1, then 0, then 1. So hence the hyperbolic cosine has power series expansion 1 plus a half x squared plus 1 over 4 factorial x to the 4th, and so forth. And very similarly, you can derive the power series for sinh is this. Of course, that should not be at all surprising. I'll add something here. This is not surprising because we know that e to the x is equal to cosh x plus sinh x. And if you look at that, if you look at the power series we had for exponential, it was the sum over all powers divided by factorial. So like e to the x was, the sum. Let's say k equals 0 to infinity of x to the k divided by k factorial. So if you look at that, that's exactly the kind of terms we see here and here, right? These are the even terms. Those are the odd terms. That's because cosh is even and sinh is an odd function. In fact, cosh and sinh are respectively the even and odd parts of the exponential function. And that's why when we look at the power series of cosh and sinh, we get respectively the even powers in the exponential series and the odd powers in the exponential series. This is not a mystery. This is just, things working together. It is neat that these are just like cosine and sine, but with no plus or minuses as well, right? There's a reason for that. It's the tip of a much larger iceberg. Now, we'll move on to slightly more complicated examples. So here I look at sine squared of x. So one way we could do this is to remember our trig identity, which is sine squared is 1/2 1 minus cosine 2x. Then we can make a substitution. We know cosine of 2x, we know cosine already, so I just take the cosine series and replace x with 2x, like so. And then I substitute that into the trig identity, right? And out pops x squared minus 1/3 x to the 4th plus 2 over 45 x to the 6th, and so forth, right? Another way we could do this would just be to multiply the series for sine. That's another legitimate technique. That's not a bad way to generate a few terms pretty fast. So sine squared is sine times sine, so if I multiply, when we multiply series, we just do it the same way you already know how to multiply things. We just collect it term by term. I would recommend starting with the lowest order. Lowest order possible here is x times x, which is x squared. Then x to the fourth, we can do x times x cubed, or we can do x cubed. Oh, I need to use both of my lightsabers. So we can do x times x from x squared, x times x cubed, or x times x cubed times x. Both of those give me a 1 over 3 factorial with a minus, which gives me, hey, oh, I put it over here, like that. So I'm distributing, actually. I'm just multiplying this x times and then I'm multiplying this. Oh, I'm not sure how I group things. I guess I was distributing. Well, that's the interesting thing, guys, is it doesn't matter what order you multiply things in, because fortunately these power series are absolutely convergent on their open interval of convergence, which means no matter how you rearrange the terms, you won't change the outcome. You don't face the trouble we do with conditionally convergent series in the Riemann rearrangement lemma, which you might have read about in your text. Anyway, multiplying it out, collecting like terms, we get x squared. We got two copies of 1 over 3 factorial with a minus. For the x to the sixth, I get this x times that, and I also get that x times that, which gives me 2 over 5 factorial. But I also get the cube times the cube, which gives me a minus 1 over 3 factorial cube, 3 factorial squared, and x to the sixth. And the minus cancels, or the minus gives me a plus there. You clean that up, you get 2/45, and so voila, which is what we derived with the other method as well, right? Again, comfortingly, math does not produce different outcomes as long as we use correct techniques. A third, it's almost like math is discovering some objective reality, which we all can understand. Funny how that is. Now, f of x is sine squared. Oh, the other method, of course, which I would discourage actually for this example, is just by straight differentiation. So one derivative gives me that, and then if I differentiate I get that. If I differentiate again I get that. If I differentiate again I get that. I assure you, of the calculus students I teach, there are very few who can get past the second derivative correctly. So I think this is a dangerous game for you guys because you're bad at differentiation, honestly. But you have to calculate pretty far to get that. You have to calculate the sixth derivative to get to that 2/45 term. That requires calculation of the sixth derivative of this, which is just a mess. So there, I mean, I've done enough differentiation to see that I get the x squared and the minus 1/3 x to the fourth. So I'll just leave you with the question, what method do you think is best? I think the question is, what's the question? These methods are all valid, and you got to understand what is the right tool for the job. Here's another example. We're looking at the square root of x around a to the fourth. So I do my differentiations, I plug in my values, and here is the square root of x centered about 4 out to the fourth order. Yowzers, that's quite a thing. Another example, example 9 here. This one's kind of silly. I like to put this one on a test just to see if people are awake. Find the Taylor expansion of this cubic about x equal to 0 and x equal to minus 1. So here's the derivative, second derivative, third derivatives. So you can evaluate at 0, or you can evaluate at minus 1, and you see what happens. So about 0, we just get back the function again, right? Because what's the best polynomial approximation to a polynomial? You know what? It's the polynomial. Now about minus 1, something kind of cool happens. This gives us the insight that about minus 1, we've got x plus 1 to the n, right? Because minus a minus 1 is x plus 1. And in this case, we get 0, 0, 0 from the evaluations we did up here. And 6 over 3 factorial is 1, so we have derived with the Taylor's theorem that this factors as x plus 1 cubed. It's kind of a cute calculation. But anyway, remember, intuitively, polynomials, power series are polynomials of infinite order. So if you're looking for power series approximation for a polynomial, Well, you're already looking at it. Example 10, we're asked to find the Maclaurin series for tangent. I just find the first two non-zero terms, so it's not too bad to differentiate once and then twice, and we get 1 for the first derivative, but these are 0. Apparently we'll need to differentiate one more time. Careful of your chain rules and power rules and such. We get 2, and then by Taylor's theorem, we get x plus 2 over 3 factorial x cubed, so we get x plus 1/3 x cubed plus dot 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 dot. That's tangent of x. Now we could differentiate further if we want to generate higher terms, or alternatively we could divide actually this power series for sine by the power series for cosine. I'm not sure if I have any of that written out for you guys, but that's another way you could do it. I'm sure it's in your text. So summary, the following Maclaurin series you should know. All right, you should know that we can expand this. I mean, this we've been using extensively in the past videos, right? This geometric series result. We learned in this video that e to the u is in fact u to the n over n factorial summed n equals 0 to infinity. We also learned that sine of u has this power series expansion, and cosine of u has that power series expansion. I'm rewriting the results with a u, with the intention that you could think about using these as a template for substitutions. All right, and this is definitely something you want to have a hard copy of for the next test. You don't want to need to find this in a video somewhere or in a PDF. We want to have this on a piece of paper that you can look at and calculate with. All right, assuming that it's an open book test. Perhaps it's a closed book test, and well, anyway, it's a different game. So for many problems, you can use these basic series rather than explicitly generating from the Taylor expansion, right? So like x times sine of x over 2. So what I do is I take x times the power series for sine with x over 2 substituted in for my u. I do the algebra, apply by the x, and there you have it. That's the power series expansion in sigma notation for x times sine of x over 2. And you could also generate it term by term, like x times that, which would give you these first 3 terms, the first 3 non-zero terms. Sometimes I ask for the complete power series expansion using sigma notation. That would be like this. Sometimes I just ask for the first 3 non-zero terms or the first 2 non-zero terms, something like that, and that's what I want, this plus dot dot notation. They each have their merit. Both of these forms have their merit. All right, well, next up is the binomial series. All right. So actually, I'm going to cut the video off here and start again right here.